Welcome back to Deep Learning. So today I want to talk to you about the actual pooling implementation. And the pooling layers are one essential step in many deep networks.
So that's stuff that's really stood the test of time.
The main idea behind this is that you want to reduce the dimensionality across the spatial domain. So here we see this small example where we summarize the information in the green rectangles, the blue rectangles, the yellow and the red ones to only one value. So we have a 2x2 input that has to be mapped onto a single value. Now this of course reduces the number of parameters required. It introduces some hierarchy and allows you to work with spatial abstraction, and it reduces computational costs and overfitting, but we need some basic assumptions of course here. And one of the assumptions is that the features are hierarchically structured, that by pooling we're reducing the output size and introduce this hierarchy that should be intrinsically present in the signal. We talked about this, the eyes that are composed of edges and lines, and then faces are composed of eyes, nose, and so on. This has to be present in order to make pooling a sensible operation to be encoded into your network. So here you see a pooling of a 3x3 layer, and here we choose max pooling. So in max pooling, only the highest number in the receptive field will actually be propagated into the output. Obviously we can also work with striding, and the stride typically equals the neighborhood size such that we get a reduced output dimension. One problem here is of course that the maximum propagation adds an additional non-linearity, and therefore we also have to think about how to resolve this step in the gradient procedure. And what we do is we introduce essentially again a subgradient concept where we simply backpropagate into the cell that has produced the maximum output. So you could say the winner takes it all.
The winner takes it all, the loser standing small.
Now an alternative to this is average pooling, and here we compute simply the average over the neighborhood. It does not consistently perform better than max pooling, and then of course in the backpropagation path the error is simply shared in equal parts and backpropagated to the respective units. There are many more pooling strategies like fractional max pooling, LP pooling, stochastic pooling, spatial pyramid pooling, generalized pooling. There's a whole different set of strategies about this. One alternative that we already talked about is strided convolution. This became really popular because then you don't have to encode the max pooling as an additional step and you reduce the number of parameters. Typically people now use strided convolutions with s greater than 1 in order to implement convolutional pooling at the same time. So let's recap what our convolutional neural networks are doing. So we talked about the convolution producing feature maps, the pooling reducing the size of the respective feature maps, then again convolutions, again pooling, until we end up at an abstract representation, and then we had these fully connected layers in order to do the classification.
There's something to what you say in some ways in which I disagree.
Well, actually we can kick out this last block because we've seen that if we replace this with a reformatting into channel direction, then we can replace it with a 1x1 convolution and just apply this in order to get our final classification. So we reduce the number of building blocks further. We don't even need our fully connected layers here anymore. Now everything then becomes fully convolutional, and we can express essentially the entire chain of operations by convolutions and pooling steps. So we don't even need the fully connected layers anymore. The nice thing about using the 1x1 convolutions is if you combine this with something that is called global average pooling, then you can essentially also process input images of arbitrary size. So the idea here is then that at the end of the convolutional processing, you simply compute the global average for all of your inputs and map into the channel direction. And this way, because you have a predefined average pooling operation, then you can make this applicable to images of arbitrary sizes. So again, we benefit from the ideas of pooling and convolution. An interesting concept that we will also look into more detail in a later lecture is the Inception Model. This is from the paper Going Deeper with Convolutions. Following our self-stated motto, we need to go deeper. And this one won the ImageNet Challenge 2014, and particular example is GoogleNet as one incarnation, was inspired by Network in Network. And the idea that they present here is, why do we have to fix the steps of convolution and pooling in alternation? Why not allow the network to learn on its own when it wants to pool and when it wants to convolve? So the main idea is that you have the previous layer and you just put in parallel 1x1 convolution, 3x3 convolution, 5x5 convolution, max pooling, and then you just concatenate them. Now the interesting thing is, if you offer all these 4 operations in parallel, that essentially means that the next layer can then choose what input to trust most in order to construct a deep network. And if you do this, then you can further simplify this. For example, the 3x3 and 5x5 convolutions, you may want to compress the channels first before you actually evaluate them. Then you find the configuration here on the right hand side. This incorporates some additional dimensionality reduction. But still, this parallel processing allows you to have a network learn on its own the sequence of pooling and convolution layers. Then you get models like this one. This is already a pretty deep model, which features a lot of interesting further innovations that we will talk about when we are speaking about architectures.
I already kind of think of neural nets as a kind of program. I think of deep learning as basically learning programs that have more than one step.
Okay, so next time in deep learning, we want to talk about how we can prevent networks just from memorizing the training data. Is there a way to force features to become independent? How can we make sure our network also recognizes cats in different poses? Also a very nice recipe that can help you with that. And how can we fix the covariate shift problem? All important points, and I think the answers really deserve to be presented here. Also have a couple of comprehensive questions. Name 5 activation functions, discuss those 5 activation functions. What is the zero centering problem? Then write down a mathematical description of strided convolution. What is the connection between 1x1 convolutions and fully connected layers? What is a pooling layer? Why do we need those pooling layers? So many interesting things that somebody could ask you at a certain point in time. We have links here to further reading, the self-normalizing networks, and the network in network paper, and so on. And if you have any questions, you can post them in the comments or send them by email. And of course, we have quite a few of references. So again, I'm clicking through them a bit quickly, but you can also read them in the description of this video. So I hope you liked this video, and we'll see you in the next lecture. Thank you. Bye-bye.